All right, how we doing, everyone? Doing good? All right, so today should have been the review for exam 3, but because of the material he hasn't presented yet, he extended it by 1 week. So instead of it being on next Wednesday, it's been pushed to not this Monday, but the Monday after that. All right, let me see. Pulling out the good old, actually we have a mouse. Go minimize that calendar. So your exam should have been on the 13th, but he pushed it to the 18th. So everyone hearing, your exam's now on the 18th. The assignment was originally, if it were supposed to be the exam on Wednesday, assignment would have been due Monday, so in a couple days. But because he extended the exam, extending the assignment up to Saturday. So is that good with everyone? Yeah. Oh, someone in the chat talking? All right, let me check out my participants. Mute your mics just in case, unless you have a question to ask. All right, so do we have any questions before we start, or comments, complaints? Everything's good?
I have a question.
All right, what's up, Peter?
So when we draw for computer assignment problem 4,
4?
do we continue the line from X then to Y then, or does it stop? When you drew it, you only had it go from X then and then to B sub 1, and it stopped in the middle. Does it need to continue on to Y then?
Y of n? Well, you need the output, right?
Well, that's what I thought, but on the one that you did, you didn't continue to go on.
Let me open up a new window. Let's go to EE360, which I have it saved right here. Let me zoom in. Assignments. And I should, wait, why did I have it? I think I gotta change that date. Yeah, that's a typo. Yeah, that's a typo. I gotta change that. Computer assignment 3. So what are you talking about right here?
4. Yeah.
4A or B?
Either one. I'm just wondering if we need to continue to the output, because when you did the example, you stopped in the middle.
Well, if we think about the impulse response, well, let me just tell you what's going on with the impulse response. So from our class, we have a box, which is h of n, right? And we have our input x of n, and then our output y of n, which is defined as the convolution of x of n convolved with h of n. So the one thing that Dr. Stevie was talking about in class was if, well, he doesn't say it, but I'm going to tell you practically what it is. If you just kick your box with some big shoot and big impulse, what happens when you throw an impulse into a system? What is the output? An impulse response, yes. So that means if this were equal to the impulse response convolved with h of n, that means what do you get out? H of n. So I'm going to do a quick example. So h of n is basically whatever we had in our system, which could be the b coefficients. Actually, let me show you here. It'll make more sense. Let's do a direct form 1, which starts off with a node, which goes into a delay. Then, yeah, let's just do 2 delays. It should be enough. And for all practical purposes, let's call this one B0, B of 1, and B of 2. Plus. So were you talking about, the output? Like,
Right there, yeah.
yeah, you have to put the output. Because, well, okay, suppose our impulse response, let's say he gives you a quiz or an exam. Like, okay, he's going to give you h of n, and it's going to be here. And this is like 2, this is 1, and then I guess 2 again, and that's it. If he gives you that. So if you kick this box, we're going to kick this box, right? So with the Dirac function, so we're going to kick into this box. So we have a 1 going in here. Okay, there's a 1. Let's think of 1 as just a big full bucket of water, ideally constant. So what happens when this 1 goes through this gain? Then the output should equal whatever this b of 0 is at the time 1. T is equal to 1, right? But this bucket of water also goes down into this delay. It's stored in here, and it goes down here. And then it keeps going down. So for the first instance, at time is equal to 0, that's what I meant to say. D of 0, there we go. At the first kick, we kick the box at time is equal to 0, so n is equal to 0. We throw a 1 here. What's the output at n is equal to 0? Just equal to that. Whatever is in the first gain, whatever gain is in this b of 0. So now we got rid of this water. It's already out of our system. But we still have this 1 that's traveling through our system. So now it's here. So the 1 went from here down to, let me grab another color, down to here now, okay? Now this one has to go through here, and then it gets stored in here. So now that the 1 goes through here, but it just flows out of our output, what is our output with this 1 going here? So this is 0 right now, and this is 0 right now. So what's our output?
1.
B of 1, yes. B of 1, and then I'm going to do this, D of 1, okay? At T is equal to 1. So that means the output at time is equal to 1 is just whatever's in this gain block. So now, okay, now the 1's traveling again. It finally traveled through our system. Now it's in here. Now it's right here. So this is 1, this is 0, and now this is 0. Okay? So now that we have a 1 here, it's multiplied by a gain block. This is 0, this is 0. What's the output? B2 of D of 0. And there you go. So the whole point of this is for an FIR filter, a fear filter, or whatever he wants to call it, for fear, the impulse response will give you all the points or all the gain blocks in your direct form 1 or your transpose direct form 1. Does that make sense? Yes?
For D sub 2, why isn't it D sub
Oh,
2?
2, yes.
Okay.
There we go, sorry. So what I'm trying to tell you guys, and the purpose of the fourth assignment, not the fourth assignment, the fourth exercise is, okay, remember how we were doing all those coding blocks? We were doing, I remember, actually let me go on another page. Remember how we were doing for I is equal to some pre-length plus 1 dot dot 1 dot dot pre-length plus 1 plus end length, right? Remember that stuff when we were coding C of n, which is equal to, I remember, C of n is equal to B of 0, X of I, B of 1, X of I minus 1, dot, 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 B of n, X of I minus n. This is annoying to code. It's really annoying to code. Okay, let me just finish this up. Y of n is equal to, I'm going to draw this in a different color. Let me see. It's going to be doing this plus, nope, not plus, minus A of 1, C of n minus 1, minus A of 2, C of, I'm literally doing your assignments now, kind of, n minus 2, dot, dot, dot. I'm going to call this one A of m, C of n minus m, okay, where n and m can be different types of poles, different types of zeros, which is a key word for a future assignment we'll be talking about. So to quiz everyone, what does this represent in code? What does this theoretically represent? When you see a C of n and a Y of n, or you see x's being delayed and these C of n's too, what do we have here? Direct form 1, 2, or transpose 2?
1.
There we go. So the reason why I was trying to quiz you guys on that, because here's our input, right? Here's our current input, but we're delaying our input. So one thing I want to show everyone is if you see an input being delayed, automatically think about it as either, actually it's just direct form 1. Whereas so this is DFI. But for DF2 and TDF2, you got a point where, you have queues. And the queues either do this for the DF1, it let's see, it pulls stuff out. Actually, I remember the one with the transpose. You B of n x of this plus a of m y. No, I don't want to do that. Actually, yeah, you can solve this for now. Solve. Where we're saving just states. I didn't solve for this one because I gotta get rushing with the point is. But point is, this is annoying. This is really annoying to write down. So the purpose of the fourth exercise is, why don't we just tune one number? And you see how this theory right here is? You see how we have this impulse response? Like, why don't we just create a code that just, depending on whatever impulse is, store it and just convolve it with whatever we have, whatever our system or whatever we want. So our codes can be really easy. So instead of these really long lines, we can just have a matrix, which is the purpose of that assignment. So what I want to get to everyone is the raw definition of convolution. So we're going to try and do number 4 again. Okay. So let me show you what I'm talking about. Let me see. How do I want to show you guys? So remember how we have x of n convolved with h of n, right? Which is equal to, well, I'm going to keep this. Which one should I keep? I'm going to keep h of n. I'm going to call it k. Times x of n minus k. And then this right here is some summation signal. From k is equal to infinity, k is equal to minus infinity. So from looking at this, here's our x of n, here's our h of n. Our h of k right here is just, well, numbers. So if this is 1, that's 1. It makes sense. It doesn't change. This one just remains constant. Okay? But the thing is, for this signal, we're flipping it. See, right here we have x of n, but our variable here that we're playing with is k. So that means this right here just flips it. Okay? Does that make sense? So if we were trying to make a code, if we're trying to do the direct form 1 block, in our code, we were going to have to, so let's say we have some x input. Then we want to flip it. Actually, let me just do it. Let's call it maybe some 1, 2, 3, right? So this is our input. And then we want to flip it. So let's call x flip, which is equal to, well, I'm just going to do this, 3, 2, 1. I'm going to call this one x flip. And now that we have this, we're going to try and get it to a form. Remember that last time I was trying to show everyone? And let me show everyone what's going on. So using this as an example, I'm going to do this. So here's our x. Here's 1, 2, 3, right? Does that make sense? 1, 2, 1, 2, 3, right? Okay. And here's h. I'm just going to call h just this 1 h, okay? So let me show what's going on. So I'm going to type in this right here, h of 0. So I'm going to look at a condition of k is equal to, no, not k, n is equal to 0, okay? We're going to look at this equation, okay? We're about to do the raw definition of convolution, and this is what I messed up last class. So with n is equal to 0, so we're looking at y of n is equal to 0. N is equal to 0. And now here I'm going to call this one, we're sweeping this. Here's k is equal to 1. So h is 0. To get this condition for n is equal to 0, well, k has got to be 0, sorry. But for this one, we're looking at n is equal to 0. So this is going to be 0. This right here is also 0, which means this right here is 0. We're looking at this first point right here. Okay? Does that make sense? So now if I were to look at this in terms of convolution, plus k of 1. So here's h of 1, but our n is still equal to 0. Here's 0. So that means here's 0 minus 1, which is just x of minus 1, right? But what is x of minus 1? There's nothing in there. Okay? Makes sense, eh? And now let me go backwards in time. K is equal to minus 1, h of minus 1, x of 1. Just to skip some steps. So right here I have, let me get another marker. The pattern I'm trying to get into everyone's head is here's minus 1, here's 0, and here's 1, right, for h's. So it's going like this. It's just going forward. But for x, and I don't have enough colored markers. Oh, I have a blue one. Our x, it's going, well, here's minus 1, here's 0, and here's 1. It's flowing like that. So what I'm trying to tell everyone is, if we were to do this mathematically, I'm going to put this right here. The graph. So this is right here is the mathematical math way. Okay, I'm going to show you what this means graphically. So here's graph way. Graph way. So in terms of graphing this, we flip x. So I'm going to call this one. So here's 1. Flip that, 2, 3. And I'm going to call this one x flip. To distinguish this, this is not the input. This is the input flipped. And then this right here is going to be h. Okay? So if we were to do this graphically, all we're doing is we're looking here, here, and we're just multiplying these points and adding them. Multiply this and add, multiply this and add, multiply this and add. And what you see is the only points that are being added or that actually are valid is this right here. Okay? So that means we only get one point that we're adding, so this right here is just a 0, this right here is just a 0. Here we get a value. Makes sense, eh? So if I were to do one more math point, let me just pull out another page. Okay. Let's pull out our input. Use green. We're looking purely at mathematics right now. 1, 2, 3. X. 3, 2, 1. And h. So, all right. If we were to do all this addition, right, what is y of 0, which is equal to, well, whatever this is, h of 0, x of 0. That's it. Makes sense, right? And this right here proves it too graphically. So we've just proved it mathematically and graphically. So now I'm going to do the second point, when n is equal to 1. Okay, we're going to shift this graphically. It should be shifted, but we're going to just do this by math. So let's start with, does it bother anyone if I just start with k is equal to 0? You know why I'm starting with k is equal to 0? Because if you noticed, here's our h, right? And h only exists when k is equal to 0 and 1, right? So we don't have to look at the negatives. We can just look at purely whatever h is. So just 0 and 1. Because it only exists for 2 points when k is equal to 0 and 1. So there's only 2 points we ever add. So k cannot be negative or past 3. Does that make sense? Sweet. So looking at k is equal to 0, h of 0, and then x of, let's pull out our raw definition, infinity to infinity of h of k and x of n minus k. But we're looking at n is equal to 1. So that means this is 1 minus 0. What is this equal to? X of 1, right? Then let me bring out another color. Plus h of 1. So this is right here is k is equal to 1. X of 1, because n is equal to 1, minus k, which is 1. And then what is this equal to? X is 0, right? And now I'm going to prove it to you. So what's h of 0? It's equal to 1. Well, there we go. I'm going to define that right there. And x of 1 is equal to this value right here, 2. Makes sense, right? And then here's h of 1. What's this equal to? It's a number. And then what's x of 0? It's this. So this is how you mathematically approach it. But okay, if someone wants me to punch in numbers, this right here is 1. Let me use a different marker. Red. 1. X of 1 is equal to 2. H of 1 is equal to 1. And x of 0 is equal to 1. So that means this right here is 2 plus 1 is equal to y of 1, which is equal to 3. Makes sense? Okay, and then if someone wanted me to prove this graphically, so this is math way. So this is just looking purely at these signals. We're not doing anything except mathematics. Now let's do it graphically. So from our first example, we flipped our input. So we have x flip. But now we got to shift it to the right due to, well, the graphical method. So if I were to draw this again, here's our x-axis. We're going to shift it. So we flip this, should be flipped, and then shift right here, 2, 3. There we go. This is 1, 2, 3. X, flip, and then we just flipped it by another, we just flipped it to the right. So everything, when we're shifting, we're shifting to the right. And then let me draw, okay, same color. Here's 0, 1, 0, 1, and this is h. So if we were to do this graphically, what do? We shift it, and then we start looking at similar points right there. We got a 0 and a 3 multiplied. And then we have a 2 times a 1 plus a 1 times a 1. So this right here is 0 times 3 plus 1 times 2 plus 1 times 1, which is equal to. Make sense? And that's what I wanted to show everyone last week, but I was like, wait, this is not making sense. But because I was looking at the flipped signal for the math way. You should be looking at the raw data when you're doing the raw definition of convolution. If you're doing this like brute force this definition, look at your actual raw data. But if you're gonna do it the graph way, then don't look at this. This will not help you. Just do it the graph way. It's okay. You take your input. Here's your thing that you're gonna keep constant. You take your input, you flip it, and then you put them on top of each other, and then. So that's another hard way. So they're both difficult in their own aspects. Yeah. Pick your poison. And
going, right?
So yeah, and if you're really artistic and you like to draw and have there's some people who have really small handwriting. They're really good. Yeah. Go ahead, do graphical. But if you like math, you can do it mathematically too. But in terms of practice, I would highly recommend the graphical way because I think the signals he's going to give you on the next exam, I think this might be it. He might just give you this. It's really random. Like, okay, just 1, 2, 3, and this. So the next thing I want to show everyone And so that was just my review of convolution. And if you wanted to finish this, should we finish it? Wanted? Actually, 1, 2, 3, 1, 2. All right, so
You just have to go until you reach 0, right?
watch this, watch this. So how many points do we have left? So before I talk about this, what's the size of this data, or how big, how long is this? It's only capital N is equal to n of x is equal to 3. We have 1, 2, 3 points. How long is this? 2, right? So there's a property called the length property where you look at the sizes.
Oh, snap.
I forget what it's called. It's the length property or something like that. Where you look at to find the final size of convolution of like two convolving signals. N of y is going to equal n of x plus n of h minus 1. All right, so point is, if we have 3 points in x plus 2 points in y minus 1, which means how many convolutions, how many things do we have to draw, or columns do we have to do? So this right here is 4. So if I wanted to keep going, we just did 2 points. That means I need 2 more to do, but you can see it already took a page, so that means I'm going to have to waste 2 more pieces of paper.
Oh, nice.
So this is how you can figure out how many things you got to draw, or how many mathematical things you got to calculate.
Oh, that's not bad. 4 is not bad.
And yeah, that's basically convolution. But point is, in DSP engineering, there's a rule. So the DSP rule, length rule, is both signals are the same size, and n of y is always equal to 2n minus 1, where x and h are the same. So if x was a signal of, it was a length of 10, h is a length of 10, that means the final one is going to be 2 times 10 is 20 minus 1 is 19. So that means your resulting convolution is 9. Your final signal is going to look like 19. Actually, let me show you one more practical example before I move on to the assignment.
Dude, that's really cool, though.
All right. Let's show everyone something cool. So, how do I want to show you guys this? If I had some signal, let's just say it's 1 and 1. Do I want to show you that? Let's call this some pulse. We're just going to look at some pulse. And then let's look at another pulse, which is probably 3, I guess. 1h. What I was going to try and say was, let me see, how do I want to do this? Let me see, because I was going to try and get to you guys something pretty cool. Because there's one thing I was going to show you, and they use this a lot in radar technology, where you have a signal that you have, like some constant signal, and you're just waiting for some pulse. So what I was trying to get to you guys, actually, whatever. So this pulse is going to come through our system, so obviously you got to flip it. So we're looking at the tau domain. So this right here is time, this is time, and now we're looking at the tau domain. So this right here just got flipped, x flipped, right? And now here's our system of interest, okay? So at time is equal to, or tau is equal to, so we're looking at tau is equal to 0. We're at this point right here. We just flipped this input right here. We just flipped it right here. At our real time, like here's our output y of t. We're not going to see anything until this square starts moving inside right there, right? Okay, and this is just a length of 1. So this is how long it's going to last. So if I were to do this, actually, Okay, let's do it. So our square starts entering into our system, okay? Right? Until we reach a point where it starts turning into 1, and this is right here is 2. So now our block is in our system. So at time is equal to, no wait, no. Oh, 0, 1. There we go, sorry. At time is equal to 1, then our signal is going to be right here, right? And I should have made this bigger. 1, 2, 3, right? So I'm going to redraw this. Here's our square, just entered our system. And now our square is going to keep moving through our system. And let me just draw it right here, right? If I were to keep drawing it right there, if we were doing convolution and looking at the area of our square, so this here is an area of 1 multiplied to another area of 1, what do we get? Just the area of 1. Okay, up until we get to right here. My square is not good. So this is our square. It's just going through our system up until time is equal to 3. Okay, makes sense, right? So right here is where we get the full area of our pulse. But now it starts leaving our system. So let's just draw this square right here. And now you'll see a point where, oh, it starts going down until we get out of our system. What's the convolution or the multiplication between this and that? It's nothing. We're doing this graphically, by the way. So that means you get to a point where at time is equal to 4, you get nothing. So this right here is our pulse. Looks pretty cool, huh? So does that make more sense what convolution is? Right here we're just doing graphically. But I think at the end of this, I'm going to show you guys a cool presentation. Actually, you want me to show you how to do this mathematically? Would you like that? Kennedy, would you like that? Yeah. All right, so to what I was trying to do earlier. I was supposed to show you guys this earlier. No, last week. But I was getting some weird symbols and mathematics wasn't working for me. So back to what I was trying to do. H of t is equal to 1 up to here's 0, here's 2. And here's our x of t. I'm going to show you guys this is really, really cool. And you can punch this into MATLAB, which we will do. Let's do this. 1 and 1. So back from the last class, this right here, what can we define this in terms of functions as of in terms of like, well, time? Actually, no, that's a bad question. So if you were to model this mathematically, what would you call this equation? H of t is equal to, well, what happens when we go from 0 to 1 at time is equal to 0? What does that function look like? What's the first functions we learned from computer assignment 1? Unit step. All right, so we start our unit step, right? But then we fall down right here at time is equal to 2, right? So how do we get rid of this unit step? By subtracting another unit step. And there we go. That's how you define pulses in all your classes. So this right here will model our first pulse. So now our second pulse is going to be in this time domain. I'm going to do this for now. U of t minus u of t minus 2. Would it be valid to call this window u of t minus u of 2 t minus 2, right? Because the function I'm about to multiply to this pulse, this window, is, well, what function's linear with 1 and 1? T, right? So at u of t, right, we just start, right? We start here. What's t? What's this value? What's the input equal to when t is equal to 0? 0, all right? But now what happens when t is equal to 1? We get a 1, right? But then this kicks in and then just kills the entire signal. We don't have a signal anymore. So this is how you would model a pulse, and you can use this in LT Spice too. So now, hopefully I don't mess this one up. We're going to try and do this mathematically. X of t convolved with h of t is equal to the big integral from tau is equal to minus infinity to tau is equal to positive infinity. I'm going to do this. X of t and h of t minus tau. So tau d tau. Okay? This is the raw definition of analog convolution. So the first thing I'm going to do is, here we have t, so we replace all our t's in our input. Here's x of t. We're going to replace all the t's with tau. Okay? So I'm going to do this. And let's call this one tau. Then I'm going to do this. U of tau minus u of tau minus 2. Makes sense, right? Okay, times. Now for this one, I'm going to replace all these, what do you call it? I'm going to add a shift. So actually we keep our signal right here, right? All we're doing is we're shifting it. So here's h of t, right? So if we ignore this right here, right? Here's h of t, right? So that means all we're going to do is just add a shift. Same thing with here. If this is our h of t, here's our t, right? All we're going to do is just add a minus tau. So in other words, u of t minus tau, we're going to shift it by tau. And then minus u of t minus 2, okay, minus tau. Is everyone following that? Okay, because for me, it actually took me a while back when I was in 360. I was like, how do you shift this? So if you just ignore this t, we're looking at our actual thing. All we're doing is just shifting it by a little bit. So whatever this is, you keep what's in here, but you just snug and tug this tau in there. All right? That's a good thing to remember on the exam. Hint, hint, this might be on the exam. So now back to how do we solve this. So how do I do this? Let's do it like this. So I'm going to look at this term right here. So this term right here multiplied to this term right here. Okay? So is equal to, I'm going to put this big integrand, t u of t, tau u of tau, times u of t minus tau. Okay? And then I'm going to do this right here. Minus tau u of tau, or u of tau, times u of t minus 2 minus tau. Okay? Now I'm going to pull out another marker. Actually, let me pull out the blue marker. You like colors? So I'm going to do this, which has a minus sign. And then this is also multiplied to here too. Right? See it? Now I'm going to multiply this to this. Okay? Minus tau u of t minus tau minus 2 times u of t minus tau, right? Okay? And now the final thing I'm going to multiply is this. Minus and minus gives me a plus tau u of tau minus 2. Yes, tau minus 2 times u of t minus 2 minus tau. Can you see that? All right. So now we have a whole mess of equations, and you're trying to figure out, oh no, how do we crunch this all into a smaller thing? This looks hard. Never fear, everyone. So I'll show you this. So if we look at this first term right here, if we were to look at this term, if this goes to 0, if u of tau goes, if tau becomes negative, so it becomes -1, we put a -1 in here. What's u of -1? 0, right? So that means we don't, for our integrand, we can just put a 0 right here. Because if we go negative for this term, it's going to just be 0. Now if we look at this term right here, for tau is greater than, well, let's say tau is t, right? T minus t is equal to 0, right? But now let's say this t, this tau gets bigger, which means this becomes more negative, which means this becomes a negative term, which means if you have u of a negative number, you're going to get 0. So that means if we were to look at this first term, the integrand for the first term is we can't go anywhere below 0, and we can't go above t. Okay? Which means these unit steps help bound our integrand. Okay? Which means our final equation is going to be tau d tau. Make sense, Ray? Yes. Now our next term. Here we have u of tau, right? And it's going to be the same methodology. So minus 0, right? Okay. But now we're going to look at this. So let's say this tau is equal to t minus 2, right? So if you treat this as minus t minus 2, okay? So we're subtracting this by itself to give us 0. But what happens if this gets bigger? If this term gets bigger, then you could have a bigger negative term, right? Which means this thing goes to 0. The unit step just kicks into 0. Which means you can't go above t minus 2. And then you start seeing a pattern, right? Minus. Let's look at this term. Now we have tau minus 2. So what if tau is equal to 2? Or, yeah, 2. That means, well, we have u of 0. But what happens if this becomes less than 2? So that means now this thing becomes negative. Or this entire thing becomes negative. You have u of a negative number, which becomes 0. So that means we can't go below 2. And then for this one, u of t minus tau. Good. And then if we look at the same methodology for this, just to skip steps, 2, and something's not right. I know what was right. Sorry everyone. So I have 1 right here. That's what I was like thinking about this. I was like, why is this not making sense? That's a 1. So this is a 1. So this is okay. This is a 1. And this right here is a 1. There we go. Weird looking 1, right? But everything should be the same. T minus 2 tau d tau. Okay? So one thing I'm going to try and show you guys, this is a cool trick when you're trying to do this mathematically, is we're looking at the differences between here and here for our unit step. So point is, remember how we were doing this graphically? And initially we don't have anything going on, right? We just have some shape just coming into our system, right? But we notice that once our square, here's a square, starts coming into our system, it's a big 1, the impulse response is a 1, multiplied by some constant value. So what I'm trying to get to everyone is, we're going to have a period where we have a constant function being multiplied to by 1, and it's just being integrated. But it only happens at a certain point. It's just a unit step. So what I'm trying to get to everyone is, this right here, we're going to look at, I'm just going to call this some delta. We're going to look at delta is equal to, when does this function begin? How does it start? When does it start? And it basically starts when you look at the top bound. I'm going to call this one top minus bot. Okay? Which is equal to t minus 0, which is just equal to t. So what I'm trying to get to you is, if we were to represent this in terms of signals and system theory, DSP, our unit step is just going to be whatever this is, whatever our difference is, okay? So same thing with here. Here's our delta, which is equal to just t minus 2. So that means this right here, this function will only kick in for start at t minus 2, right? And then this right here, if you were to look at it, here's a delta t, and this is what I came up with, and it actually works for some reason. T minus 1, okay, we're looking at the top bound minus the bottom bound, okay, which means the unit step, when we do this multiplication, we're going to have to tack on a t minus 1, okay? And then this function right here, here's our triangle, t minus 2 minus 1, okay, which is equal to t minus 3, okay? Which means this function here kicks in if you wanted to draw some poles. Maybe I'll show you guys in code. But this is something I looked, and I'll prove this to you in MATLAB. It's really, really cool. So doing the mathematics for this. So this right here is just x dx. What's the integral of that? Just x, or tau squared divided by 2. And then if we look at our bounds, 0 to t, then what's this equal to? T squared over 2. But then we got to tack on this unit step, u of t. That's when it starts. Oh, there you go. That's when it starts. Okay? Minus. So now if we take an integral of this, t over 2 from t minus 2, 0, right? Which means it's going to be t minus 2 squared 2, and let's just tuck it right there, u of t minus 2. Okay? And now let's do this one right here, t squared over 2 t and 1, right? Which is equal to, I'm going to put a minus right here, put a big parentheses, t squared divided by 2, right? Minus, because we have this 1 right there, 1 divided by 2. And then this right here is being multiplied by u of t minus 1. Make sense? This is when it starts. And then this final one is a plus. You guys want me to skip steps? T minus 2 squared divided by 2 minus 1/2. And then this right here is multiplied by u of t minus 3. And we're going to prove it in MATLAB. That took me a while. Alright, so if I were to pull out MATLAB, so remember that last time we were doing that quiz in class and I showed you digitally what it represented? So let me pull that out. Let's see. This right here, remember how last class, and everyone saw it in class, we did this and we got the answer in MATLAB? And what I was trying to get with everyone is, when you do something digital and analog, like digital stuff actually is much easier when you think about it. You can relate this to the analog and predict what you're going to look at. So the figure that we're going to look up, well, for everyone who's here, ta-da, it's on the board. Okay, because everyone's probably wondering what I was looking at.
The chat hasn't been saying anything.
Yeah, I don't think so. They can see my video thing. Whatever. Oh yeah, is the chat talking? No, it's okay. But back to proving our quiz. We're going to use MATLAB to prove this. So the first functions I'm going to create is, and I'll show everyone how to do this too. Let's call this figure 9. Save as, call this 9. Everyone have this. So I'm going to do this in the time domain. So when you're doing stuff in the time domain, you have to, well, I do this some precision or something like that. You can call it whatever. I call it prec 0.1. Okay? And then I set up a time. I'll show you what this does. F9. I can't press F9 on my computer because I'm afraid to turn off. And then you start seeing this. Right? Now we just created time. Okay? So I've created some code, and you guys can actually use this if you have any problems. And I did this in EE360D. I was showing everyone how to create unit steps to prove their calculations, their Laplace transform stuff in MATLAB, and it was possible to create unit steps. This is how you create it. So here's how you instantiate u of 0. So at u of t is equal to 0, right? So I just have 0 zeros. There's no zeros in the beginning, and it's just a full-on 1, right? And then I create more 1s up to however long the signal is minus 1. Does that make sense? So now, I'll get to everyone. Okay, let me just show everyone this unit step. I call it U0 because there's no delay. It just starts at U minus 0, just U of t minus 0, U of t. It's a step function, so let me run that. Oh, where'd it go? Wait, oh, run that again. So there you go, right? So you see this one right here, right? How do we create u of t minus 1? So if you go here, let's zoom into this right here, right? How many points do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We have 10 points before this x of 1, right? So that means we have to add 10 zeros. But consequently, we have to subtract 10 1s from our 1s function. So right here, I created this. We're going to create 10 zeros, right? 10 zeros for here, right? But for this 1s thing, right, I have the same function right here, right? And all I do is just take away 10. Makes sense? And then we have the following. And there you go. Now it starts at 1. And now you can create unit step t minus 2, t minus 3, and the list goes on, right? Makes sense.
Nice.
And then let me show you our impulse response. H response. Oh yeah, did you see how I autofilled that? So if you want to write code pretty fast, H res, right? And if you press the tab button, completes it for you. Cool, huh? So let's watch the H response, and that's our impulse response. That's H of t, and it ends at 2. Okay? And then to create the t, right, all I did was this. It was weird how I came up with it, but and that's probably why it didn't work. No, I think it worked. Yeah, never mind. Let me show you x. X. And there you go. If you were to make this wide, there we go. From 0 to 1, we get our t function, just our pulse. Cool, right? And now if you wanted to do the brutal math, let's punch this all in. Is it going to let me do it? Okay, yes, we can. Dr. Baker won't do this for you, though. Like split screen this thing. You have lecture on one side, code on the other. Wouldn't that be cool? Yeah. So I'm going to type in this first equation. I was actually doing some stuff earlier today, but let me just show you this. So we're going to do t dot times squared, right? Divided by 2. And then I'm going to multiply this entire thing times the unit step. It starts at time is equal to 0. Okay? And now the second term that I have, and I'll erase this. Go. Let's do t minus 2 dot times, or dot power squared, and that squared term is divided by 2, okay? But this entire term is multiplied by the unit step that starts at u of t minus 2, okay? That's what I defined in my code. But there's a minus sign, as you can see. There's a minus sign right there, which means punch a minus right there. Cool, huh? There we go. And let me just, I have OCPD. There we go. Plus, there we go. And double OCPD. There we go. Then let's do the same thing for this function. We're going to do this term right here. So let's do t dot times squared, okay, dot to the power of that, divided by 2. And this term right here is subtracted by 1 divided by 2. Okay? Make sense? But this entire term is multiplied by the unit step that kicks in at u of t minus 1. Okay? Which I defined as u of 1. And it's got negative. Cool. There we go. And let me just stretch this puppy out. And then let's do our final term. So you can do this in MATLAB, and it's really, really cool. The analog version. But when he does the analog stuff on the quiz, he's going to give you something really simple like a pulse. So he's going to convince you to do it graphically. Because to even get this is kind of tough. I'll tell you that for now, personally. But I'll show you how you can do this in MATLAB and hand calculations for anyone who's going to use this on the exam. So final thing is, I'm going to copy this because we got to get going. This right here. And then I'm going to put this. Oh. Should I skip steps or no? Nah, I can't see that. Okay. T minus 2, right? Which is being squared. And this entire thing, the square, is being divided by 2. Dot 2, okay? Wait, there we go. And this entire term right here is being subtracted by 1/2, okay? But this entire term is multiplied by that unit step. Dot times u3. Who's ready to prove this? Y of t. Does that look like the shape we did last week? Does that look like it? Remember that? Okay, let me see. This is page 5, this is page 6. And page 7. Remember from last time, and I think I still have that quiz up here too. Quiz 5 stuff. Is that it? I don't remember. But remember from the last time when we were doing that, was it this, right? And I had that same pulse, 0, like this, right? And remember the shape was like this. It was like, oh, we started here and it gets exponentially bigger, and then it just stays right here, right? And it goes down like an RC filter. Remember that? And then how this right here, this 10 is equal to the area of this multiplied by this. It's the area, so if you multiply this and this, you get the area. So if this right here was area of 3, we figured out actually no. The area of this right here was like 10. A is equal to 10. That's how many points. If you add 0.1, 0.2, 0.3, all the entire signal, you get 10. So that right here was 10. And we got the shape. What I'm trying to prove with the analog case is we get the same shape. Where the point right here, this amplitude is equal to the area. And what is our shape? Our shape is a triangle. So what is that? Base times height. And that should be equal to 1/2. And now we proved it in MATLAB. Oh, so that's what I try to get to everyone on the quiz. So point is, what I'm trying to tell everyone, and the signal I gave here is actually much harder, or I can't point. This right here, the signal right here I gave you guys is much harder than was going to be on the exam. It's probably just going to be a small square. But now you have two ways of proving this on your exam. One, which is graphically, which is using this method, and then the other, which is brute force mathematics. Really freaking cool, right? Oh yeah, before we end this class, let me show you one more thing. What if you wanted to see a clearer line? Let me see. So you see that right there. Actually, that's not right. This is an analog signal. Looks cool, huh? So that's what I try to get to everyone. So I know it's 6:40. We still have an extra week for the assignment. So if you guys have any more troubles, just keep on going. But a tip I want to get to everyone before I close off is for the assignment. What I was trying to get to everyone is try to make, if you can make H response B0, B1, right? ... B of n, right? Try to, if you're trying to make your convolution signals, right? If you try to add another point at the end, try to make your code or whatever you're trying to do, your flips or your x's, like here's your x. I think your code's going to look like this: 1 something up to length of h, right? Try to make it to where whatever you do to your h, your x is a function of, is dependent on h, which is what the entire point of this system, of the signal of the assignment is. So that means instead of this really long code we did in the beginning, let's see, where is it? So many papers. So instead of something really nasty like this, try to do something where if you add another point to your impulse response, like here's your impulse response, right? And I say, hey, let's just, for fun, let's just add another point, that your x is dependent on whatever you put in your h and your code too. So same thing with your q's. You're going to do a similar methodology where it's going to be 1 length of h. And then you never have to code hard ever again. So that's the whole point of this, of that second half of the assignment. But if anyone else has questions, you guys still have an extra week, so I wouldn't sweat. You guys have an exam to study for, electromagnetics, right? So that's why I say, yeah, don't worry so hard. Questions, let me know next week. Anything else?
No, that's all. Thank you.
All right, everyone. Good night.